Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Musical. We'll look at some of the connections between math and music. A student of mine double majoring in math and music was once told, "That's crazy, those are opposites of each other." Many would agree, but the medieval conception of the mathematical sciences consisted of arithmetic, geometry, astronomy, and music. We'll look at some aspects of music synthesizers, a connection to photography, and a musical illusion. We'll start way back in time with Pythagoras. The story is that he heard musical notes in the hammering of metal rods. One rod produced one note. A rod of twice that length produced the same note an octave lower. More recently, Blue Man Group has a lot of fun banging on PVC pipe drums. Mathematically, we model this as sound waves vibrating more rapidly or less rapidly. The shorter length of one pipe produces a shorter basic wave, creating more waves per second and a higher pitch. The sine and cosine functions model such a wave perfectly. Suppose you have sine of t, where t is chosen so that there are 220 vibrations per second. We say that the frequency is 220 hertz. You would hear the note A below middle C. The wave 2 sine t would be the same A, but louder. The wave sine of 2t vibrates twice as fast, now 440 hertz, and would be heard as an A again, but an octave higher. So we can describe changes in pitch and volume easily using sine functions. What happens if we combine two basic waves? Here's the graph of 2 sine of t plus sine of 2t. Surprisingly complicated, isn't it? Notice that it still repeats, and in fact has the same frequency as sine of t, 220 hertz. So we would hear an A, though richer than before, and perhaps of some uncertainty as to octave. We can show its spectrum, which is the bar chart showing which frequencies are present in the wave. We have spikes at 220 and 440 for 2 sine of t and sine of 2t respectively. Spectra are ubiquitous in astronomy, physics, and chemistry. Well, that's enough basics to look at the music synthesizer problem. Here are 4 complicated waveforms representing some spoken vowels from the enjoyable book Who is Fourier. To mimic the EE sound, we could find a combination of sine waves to add up to this graph. Or could we? Is it really possible to recreate any graph with sine waves? Amazingly, yes. Well, there are some restrictions, but they don't apply to most sound waveforms. The combination of sine waves matching the target wave is called the Fourier series of the target wave. The square wave is a basic wave used by music synthesizers and one with a nice Fourier series. Here's a surprise. Take enough nice smooth sine waves and you can produce the sharp corners and jumps in the square wave. Here's its spectrum. 2 sidebars here. An equalizer gives you knobs that essentially adjust the coefficients of the Fourier series of the waveform. Since higher frequencies correspond to higher pitches, increasing the coefficients of the later terms in the series is equivalent to boosting the treble on an equalizer. Also, you may have noticed the overshoots-undershoots of the Fourier approximations. This is known as the Gibbs phenomenon and has a surprising manifestation in the episode Photographic. Here's a surprise from the psychologist Diana Deutsch. What do you hear? Most people hear a continuously rising sequence of tones. In fact, it is a 7-note repetition. And here's a continuous version of it, known as the shepherd tone. It's the musical analog of M.C. Escher's ascending set of stairs. You can produce a similar effect with multiple hands on a piano. Strike several octaves of A simultaneously, then several octaves of B. The pitch will seem to go up slightly. Keep going to C, D, E, F, G, and then back to the original A. Each step will sound like you have gone up in pitch from key to the adjacent key. Since the multiple keys produce several octaves at once, the actual octave is ambiguous, and your brain is likely to pick out the simplest transition from one note to the next. G is up one step from the higher A. That's simpler than G down 6 steps to the lower A. This is known as pitch circularity and is one of several illusions at Deutsch's website. The scale illusion shown here is similar and works for many people in mono. Stereo headphones are recommended though. The up-down pattern at the top is played, red in one ear, blue in the other. The notes could be arranged to the middle pattern, but on a mono computer speaker, I hear the blue pattern in C. Well, maybe it's the red pattern that I'm hearing. Try it out on Deutsch's website. The study of music, how we perceive sound, which patterns are pleasing to us, and so on, is fascinating and very mathematical.